Welcome. Today we're going to talk about critical points. They're very critical for what we're going to do next. Okay, that's a silly joke. But truthfully, a good question is, what is a critical point and why do we care? So we're going to answer that, and then we'll do some examples of finding them. So the first thing to do is wonder what a critical point is. In essence, a critical point is where a function that has a derivative, or almost always has a derivative, where the derivative is 0 or the derivative does not exist. That's what a critical point is. Often when we say critical point, we mean the x value. Sometimes when we say critical point, we mean the x and the y. It's an ambiguity in notation or semantics. Really, we want that x value, and maybe we throw along the y for a ride. Now, why do we care? Take a look at this graph. Let's find out where the derivative is 0 or doesn't exist. So I'm going to use my hand. My hand is the slope. When the slope, which is the derivative, is 0, we'll stop. So right there somewhere, there's a derivative of 0. Keep going. Now it's positive again, it goes to 0. So somewhere right about there. Then it comes down, it's negative, and then we get an angle. So now suddenly the derivative kind of stops for a second to reset itself. So we have a non-exist derivative right there. Goes up, and now there kind of is a derivative here. It's a vertical tangent line, which means the derivative is essentially infinite. We say when the derivative is infinite, it doesn't exist as a number. And it's kind of hard to talk about it. That's another point. So then we come around here, there's another one right here. And we kind of go around, there's another one here. Now, why do we care? Why do we care about this? Look at these points. They're the interesting points of the graph. They're not the only interesting points, but they're primarily the interesting points. Every local min and every local max is on here. There's a theorem that says every local min or max occurs at a critical point. That's why we care, because the local mins and maxes are interesting points on the function. So, are they all maxes and mins? No, this one, it's just flat for a second. That's a max, that's a min. That one's not a critical, that's a critical point, but it's not a max or a min. Max, min, some of them are, some of them aren't. How do you tell which ones are and which ones aren't? You can look at the graph. There are other ways. We're not going to talk about that now. We're just talking about the critical points and how to find them. So that's why they're important. Here's an example of a function. I've drawn the graph. You can see interesting things are happening. If you look at that, you might even be able to guess. There are 1, 2, 3 critical points. Okay, that's what the graph suggests, but let's actually find out if they are. And how do you do that? That's where the derivative is 0 or doesn't exist. So let's find the derivative. The derivative of this. This one is maybe not the hardest function in the world, but we can take a derivative. What do we get? 12x cubed minus 12x squared minus 24x, and then that goes away. Now, if you look at this, you wonder, where is that 0? Where does it not exist? Well, not existing means you have to do something weird, like taking a negative square root or divide by 0, or, well, trigonometry has some non-exists too. But polynomials are very well behaved. They exist everywhere. So the only critical points are going to be where this is 0. How do you solve this? This is a cubic, so you can't just plug into the quadratic equation or anything. You need to factor it. And hopefully, this very well chosen one, you can see a factor. Try it out. Hopefully you saw. We can factor out 12x. Well, if I do that, I get what? X squared minus x minus 2. Now, that factors more. 12x times something, that's going to be x, what, minus 2, and x plus 1, does that work? Yep, that works. So now, we can solve this. Since it's something times something times something equals 0, 0 is magical this way. That means this one is 0. Or this one is 0. Or this one is 0. So what do we get? Well, we can make this 0 if x equals 0. this one if x is 2, and this one if x is minus 1. Some processes you need to go back and check. In this case, that means this would be 0, 0, 0. This would be 0 for any of those. These will all work. We expected 3. And that will be our answer. Let's try one more. I'll have you try it. But looking at this graph of x over e to the x, it comes up and then kind of comes down. We're looking at probably one critical point there. Let's try it, see if you can get it. Okay, let's see. We want you to take the derivative and find out where it's 0 or it doesn't exist. So the derivative, this is the quotient. So quotient rule, derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. I'm going to simplify that. I think it's useful to simplify. I'm going to factor the top. I have an e to the x times a 1 minus x. The bottom I have an e to the x times an e to the x. Now I could cancel. I'm not going to bother because it doesn't actually matter. I'm going to leave it like this. I need to see where this is 0 or doesn't exist. Where is this 0? Well, a fraction is 0 when the top is 0. And a fraction doesn't exist when the bottom is 0. If they're both 0, we have another issue going on, and we don't have to worry about that. But if they're both 0, it still doesn't exist. So we want that one too. So top equals 0. I've got two things multiplied together. I want them to be 0. So either e to the x is 0, or 1 minus x equals 0. Now, e to the x is 0. Now, if you remember the graph of e to the x, it goes like this. It's always positive. This is never 0. There are no solutions to this particular equation. Does that mean we've made a mistake? No, it doesn't mean a mistake. It means this particular thing can't be 0. If I had a 2 right there, I wouldn't expect that to ever be 0. And e to the x, while it's not a 2, it's not a constant, it's never 0 either. So it's okay. What about this one? This one makes x equals 1. We have exactly one solution, and it is at 1. That fits our graph nicely. Our answer is x equals 1. Finding critical points is usually not that bad. Figuring out what to do next, that's for next time. Until then, this is Dr.